as I told you, I took some example from your question and answer. Before jumping into today's topic in crystallography, I briefly mentioned about some question relevant to you, also relevant to today's issue of learning crystallography as a language. Here, practical research planning and design book cover, chapter 5. What's the title of chapter 5?
Planning the research.
Planning the research was title of chapter 5. From that chapter, we have questionnaire like this. When a question arises in the mind of a researcher like you, you are doing your master's degree research or PhD degree research. The first step you should take is like this. Which one will be your own answer? Hold it and I'll ask you person by person, and I'm expecting your own supporting claim. What about you, Muhammad? You took this coursework already last year. Interesting. Let's see what he has in his mind. Although the questionnaire itself, as a self-assessment quiz from this book, has correct or wrong answer, but for us, we are not taking this coursework, so it's free, with your own claim or with your own reasoning or thinking.
Third one.
Oh, third one. Anyway, you have third one. Why third one? Because lengthy or
no. This is the basic step. Then others are quite later steps.
Earlier, later, according to your book knowledge. But what about you, Doti Mui?
I think the first step, same answer with Muhammad. I think we can start from the problem in research and convert the question into the clearly stated research problem.
You read the answer. Yeah. Convert the question into clearly stated research problem.
Yes.
That touched your heart. One thing more, comment.
Because convert the question into a clearly stated research problem. For the research, we should have some problem.
Well, what is the difference between problem and question?
Question doesn't have the orientation to resolve that problem. So problem has some trigger, some orientation. It will start some work, motivation of some work to follow that.
That is Muhammad's comment. What about your own comment? What is your own choice? Before and after?
Before was the first to commence a search of the literature.
Commence is starting. Yes.
Start. So like if we have a question, so we start. We get the basics of it, that how we can solve that question. So we do the literature study, but actually it's not correct.
What was the correct answer according to?
The third one, convert the question.
How did you know that?
I got the result.
Because you got wrong for your own answer.
Yes.
You assume that correct may be 3.
No.
Third one. Even you checked the correct one.
Yes, I checked.
Okay, I see. And I'll not talk about which is correct or wrong, but I'll talk about something in different perspective. Here, as we clearly stated, we have statement like clearly stated from this particular book, chapter 1, what is research and what is not research. I was really concerned about the word articulate. I'll talk about articulate and articulation later, but here articulate is old word from, according to Webster's 9th Collegiate Dictionary, It was used as the first time 1586. Meanings are like this: divided into syllables of words meaningfully arranged. Also, second one, B, is very appealing to my heart. Able to speak. Sometimes ago with you, I was talking about speak unspeakable, think unthinkable. Even with Doti Mui, we discussed something like that from other coursework. So, this one, if we speak something according to our own need or within our own thinking framework, we are already capable to do something. But unless we are able to speak about something, we cannot control the thing, so even we cannot imagine something. So thinking unthinkable and speak unspeakable are main motivation for me to teach you something about crystallography. Anyway, crystallography is kind of foreign language, so even if you know some symbols like 1, 2, 3, 4, 6, 1, 2, 3, 4, 6, and slash and bar, unless you know the meaning of its combination, you cannot understand the symbols or the problems. But once we master vocabulary, we should be able to speak what we have from the original research paper. Here, if I say this word in another way, using the word articulate or articulation, we need to convert question in articulated manner to express what we do not know based on what we already know. So not only in crystal but science in general, as an educated person, we are already very much educated. Normally, even university education is high-level education. You already passed through university education. You are doing master or PhD degree education. So we should be an expert about manipulating the knowledge. You should not just learn some knowledge. I'd like to emphasize at this point, you should be good at manipulating the knowledge. Especially, you should not be limited in what you already know. We should be able to express something what you do not know in terms of what you already know. What you already know should be your language. What you cannot know yet or what you do not know yet is kind of application area. Okay? You should separate these two. Language, core strengths. Application, kind of area, research problem or research area. Always at the front, as a frontier of science or technology, we will be challenged by something we didn't know beforehand. But we should be able to explain the problem with our own language. Then we can get some help from some expert in each field, although we cannot be an expert of all fields. Last time we talked about proteomics and proteins, and we talked about something like that. Engineers. So, when I read this paper, I'll talk about this paper later, but anyway, let's start our topic. Fundamentals of crystallography. Very great. Fundamentals. Within this part of textbook, we have mainly two chapters, crystal geometry and diffraction basics. If I read textbook, because I'm very familiar with whole vocabulary, it was easy, but to explain those terms to you was not easy. I'm talking about last meeting. Even distinguishing P1 and P1 was not easy, so I did make some articulation. I'm talking about language articulation, not just speech articulation. So I decided to have questionnaire like that. Explain as much as you can between from the first row, P1 and space group P1 and point group 1. So also you have something more in terms of lattice parameters and some symmetry information. That will be your final quiz. But from the textbook, I'll tell you something about this. Crystal geometry is mostly from real space symmetry. Diffraction basics is mostly from at the beginning of this chapter, mostly from physics, scattering physics. But in the textbook, there is little effort to join these two chapters. So last time I spent a lot of time to link concept from crystal geometry and concept from diffraction phenomena. Okay? And I realized these things. Linking was not done properly in the textbook. Linking these two concepts is my whole effort for this coursework. Also linking, I found the word linking has something with the word articulation. Articulation as a noun is like this. First definition, action or manner of joining. I made a mistake, not jointing. Jointing can be also good, but I meant joining, but I don't actually remember jointing or joining. Jointing is another good word for joining anyway. Jointing and interrelating some concept according to this dictionary. So articulate as an adjective, articulation as a noun, this was invented earlier than articulate. Also we have verb, articulate. Same spelling, articulate as an adjective, same spelling articulate as a verb. We have both words from English dictionary. Anyway, I'd like to introduce the word articulation and its variant in terms of linking. Simple word is link. Actually, the word articulate has more from wiki and dictionary. I'd like to spend some time with the word articulation because of the importance of language articulation in science. Okay? Then in such a way you can be helped or you can have better motivation in terms of understanding the textbook story. That is my wishful thinking. And articulation, the word articulation from Merriam-Webster online dictionary, joint or juncture. So jointing is also making sense, not only joining, but also jointing. Joint as a noun and joint as a verb, like articulate as an adjective, articulate as a verb. But here joint is noun, but not adjective. And this same definition, action or manner of jointing, jointing may be correct. But joining is my language. Jointing is dictionary definition. Action or manner of jointing or interrelating for us some concepts in crystallography or in science general. State of being jointed or interrelated. Once it was interrelated or linked, it can be a description about state, but mainly we will focus on our action and our manner of jointing somewhat unrelated one beforehand. That is the point I'd like to share with you in terms of studying the paper like that or textbook like our biomolecular crystallography. In the book we have many materials. It's too many or too much, so overwhelming or embarrassing us. But I'd like to eliminate some burden I'd like to let you focus on something fundamental in terms of what is interrelated, what is very basic for us to utilize crystallography as our research tool. Anyway, beforehand, I have an idea of active manner of articulating sounds. This is about speech articulation. That's the very definition I had beforehand, before studying the book, Practical Research, also before thinking about language articulation for crystallography. But anyway, this is about speech articulation. This is about language articulation to me. Okay? Even at the word articulation, I found many definitions from Wikipedia, even many fields. Linguistics, not only linguistics, but also engineering and other use like this, anatomy and architecture, botany and education. Many areas use the word articulation in variety of ways, but mainly articulation has something with joint in terms of physical structure. So without having joint, it's not easy to control some mechanical part. So to make such a control possible, we introduce articulation in vehicle or articulation in some architecture. But in speech, we have some sound organs, tongues and lips and yes, so throat. And so we should make some effort to make our speech be understood by others like you. For me, you, you, me. So language articulation, speech articulation. Speech articulation is limited in terms of speech organ, but language articulation requires our thinking and writing. Okay, so in such a way, I'd like to introduce the word articulation for you to study crystallography as well as science general. So for me, learning crystallography can be very beneficial to let you think the science itself, the way we can do science. Crystallography has many detailed knowledge about vocabulary and mathematics and physics, but it can be an instrumentation or instrument for you to deepen your knowledge about the way you do knowledge and science. So let me come back to the paper I gave you. This paper has some nice point about in terms of motivating you. Especially, I was caught by this paper because of this sentence. Purpose of this article is teach non-initiated persons or teach not motivated persons, primarily like Sabah, primary structural biologist, but research student from proteomics, your case. How to interpret information contained international volume of international tables for crystallography, volume A. Volume A is for symmetry, but symmetry in real space, not reciprocal space. There was one of the problem. What is real space and what is reciprocal space or diffraction space?
Real space is like
using simple terms, you already know something about crystallography, like intensity or density and symmetry, and who can explain? I'm asking about real space symmetry and what matters in real space symmetry.
Structure factor.
Oh no, sorry. Very prompt answer, but wrong answer. So, I didn't talk about reciprocal space because of A. Volume A, I told you, volume A is about real space symmetry. And volume B is about reciprocal space symmetry or diffraction symmetry. Now you gave answer structure vector, but structure vector is not about real space. So, which can be correct answer in this case? Our vocabularies are very limited. Here, not here, but if you read first sentence of introduction, crystallography is a peculiar science, strange science, at the same time interdisciplinary, and the language of crystallography is not really difficult. This is their claim, but it's very exact and must be learned. Now you learned something about crystallography. I already told you many times, vocabulary in crystallography are very few, not many. In terms of Fourier transform, we have two functions.
Electron density.
Yes, density, electron density. So, in real space, we are concerned about symmetry of electron density, okay? Simply density. In diffraction space or reciprocal space, we are concerned about symmetry of
diffraction data.
Intensity, okay? So, I'll repeat again the statement in introduction. The language of crystallography is not really difficult, but it must be learned. Also, I'll show you this again as a review. Oh, this is too many. I'll show you this first. This first, okay? This is the figure from chapter 1. When we do diffraction experiment, we are collecting intensity data. Okay, this is about diffraction space or reciprocal space. Once we get intensity data, we should convert to electron density like this. Okay, so intensity and electron density. That's the two functions we are concerned, nothing more. But if you add something more, we have actually two pairs here. Structure vector F squared is the intensity. So intensity and structure vector are two pairs. Electron density, I'll introduce some more vocabulary here. But this is not really from fundamentals of crystallography part, but here. This is something with your own quiz today. Structure vector FHKL, intensity HKL, electron density at XYZ, and Peters function at UVW. This is beyond of our current topic, but just to be symmetric in terms of its symbol, also in terms of its role, I introduced total 4 functions. Function of HKL. HKL are integers. Function of XYZ or UVW, they are fractional coordinate. They are I should not say equivalent, but they can be in same scale between 0 and 1, depending on the length of A, B, C. So-called fractional coordinate XYZ and UVW. But I'd like to reserve Patterson function for later chapters. But right now, just understand electron density function rho and Patterson function P have coordinate in fractional coordinate system. Okay. Likewise, intensity IHKL, structure vector FHKL have coordinates in integral system HKL. Okay, there are 4 functions you need to study in crystallography. Nothing more. Only 4 functions. Okay. Also, in terms of relevant symbols, this is relevant symbols for structure vector. point group. Okay, these are symbols for point group, also point group for structure vector, FHKL. So this is group or symbols for structure vector, and Laue group are symbols for intensity. Then you may have question, why do we have intensity as Laue group and structure vector as a point group? Do you know the difference between the symmetry of Laue group and symmetry of point group? If I'm key, let's take some pause here. You may need to understand. And this one for later chapters, but this one we already studied something, also we talked about something here.
These are in reciprocal space, so that's why inversion and mirror planes are involved.
Yes, that is exactly what I'd like to hear from you. Here, forget about the name point group or Laue group. Let's focus on symbolic difference between these two columns. If we pay attention to difference between these two columns, first row is 1 versus 1 bar. So difference is bar on top of 1. So bar means inversion. Here second row 2 versus 2 over m. Over m means mirror, so two-fold axis coupled with mirror result in inversion. Okay. So likewise, we should have 2 over m, 2 over m, 2 over m at the third row, and fourth row, 4 over m is okay. But here 4 over m, 2 over m, 2 over m. That's what I wrote beforehand. And here 3 bar, 3 2, 3 bar, 1 m. But here, actually, I didn't really understand why we have 3 2 here and 3 bar 1 m and 3 bar m1. What I'm thinking, why? That's the point I need to study for myself. I need to confirm, because I found many mistakes from textbooks, sometimes even from this paper. This paper, it's not completely incorrect, but in terms of symbols, I found some minor inconsistency or a kind of typographic error. If you look at table 2 of the paper, you may see something like that. At tetragonal, here I'd like to take your notice here. Here 4 over mm. Last time I did say this is something wrong. 4 over mm from the textbook table, and here 4 mm or 4 over mm. We have some space and mm. First symbol came from textbook, second symbol came from table 2 of the paper. Here, the space between 4 over m and mm, I think it's kind of typographical error, typing error, or typesetting error. It should be written like this: 4 over m, m, m. But to be exact, that can be 4 over m, 2 over m, 2 over m. That's what I wrote beforehand. Okay. So even for expert like the author of the textbook or authors of this paper, we can make mistakes. Please forgive us. Forgive teachers. You should be at the level of teachers from now on. Okay? So for like this, I need to check something behind this distinction, 3 bar 1m and 3 bar m1. As I understood, this should be like this: 3-2. Their point group 3-2 was introduced. 3 difference between 3 and 3-2. 3 is like 3-1-1. 3-2 can be written in this way: 3-2-1 or 3-1-2. Okay, this is a little bit tricky. If you read the paper, there is expression about trigonal setting, so it's technically a little bit demanding. So today, I will not introduce such a difficulty because we already have some difficulty to understand very basic understanding between 1 bar, P1 bar, and P1. But anyway, I'm trying to explain my difficulty to organize some information provided in the textbook and in the paper. So once I parsing such discrepancies, I'll be better teach you. That will be my job in the time being. Okay? But you will focus on the very basic first law today, and later part can be described or learned again in later chapters like data collection and practice. To collect data, diffraction data, we should be able to determine firstly Laue group, then space group. But generally, and as very basic, we can understand crystal bit only in triclinic setting because this is very general. There is no limitation in ABC, alpha, beta, gamma. So this most general case. Once we understand most general case, this is kind of extra. Okay. Let's go back here. Here, black box crystallography. So my question to you is, will you do black box crystallography or will you try to understand some very basic as I'm trying to teach you? But I will tell you something about my motivation for your study in crystallography. My motivation is like this. Black box crystallography, you can use some software without understanding any kind of crystallography vocabulary. That is also possible. Even if you read this paper, such a practice was discussed at the end, the conclusion line. But what can be a problem in such ways? What is your own experience, Muhammad?
I think learning the basics is more better. Learning the basics is better.
Learning
than black box.
the basics can be better.
Yes, than black box crystal.
Why?
I'm talking about my case.
But you didn't solve any structure yet.
Yes.
Even you didn't get any crystal yet.
Yeah.
But how can you talking about?
So in the future, I may have some troubleshooting problems. So just the blind idea, just black box case, I may have more chances to trap in the problems.
What about your case? I'm not talking about crystallography itself. I'm talking about motivation to learn some basic vocabulary crystallography. Also, your case, some vocabulary about doing the research itself, methodology. So, what can be your own motivation to learn crystallography, even continuing in next semester? Any learning means we will not be satisfied with black box practice. We would like to learn something very basic. Why should we need to learn something basic and how it can be useful? From the perspective of your own motivation.
I think any knowledge is useful. So like if we are getting this basic knowledge that what is crystallography basically. So it's good to learn, good to know. And also I have some interaction with Muhammad and other, we have a lab meeting. So if they discuss some kind of problem, maybe I can get some idea if I have some basic knowledge about crystallography beforehand.
You are close to mine, but I'd like to articulate my own answer for Mui. Now, comment?
No, I think seems about each knowledge very useful for each person, especially related to protein area. And in my case, it's really useful for me when I refer some kinds of paper related to this area about the
protein crystallography,
protein structure or protein function. So I can have a deep understanding after that. It's maybe help you to get some idea for my own experiment. I think so.
So if I articulate my own answer for you, any two directions in terms of motivation. Motivation as a teacher and motivation for student. As a teacher and for student, either separate these two. Motivation as a teacher, I already told you, I'd like to take crystallography as a hard science. I said hard science. Crystallography is not soft science. In this paper, it was said like this: crystallography is exact science. Without learning basic vocabulary, we cannot understand anything. Okay? So we need to understand basic vocabulary crystallography. But once it is mastered, we can discuss something about crystal engineering or protein engineering, as you said. Okay? So motivation is like that. As a teacher, I'm taking crystallography as an example for hard science. Biology is generally soft science. Biology is not that much exact. Biology has little overlap with mathematics. We have some statistics, but little. We have some informatics, but you can do biology without understanding very much informatics. So biology is closely related to human language rather than mathematical language. So soft in that regard. Okay? But crystallography is more related to mathematics rather than human language. 1, 2, 3, 4, 6 have some exact meaning, like a rotation angle. And FHKL and intensity HKL has some exact mathematical relation, square root of intensity resulting in magnitude of structure vector, like that. No other way. But for you, that was my motivation as a teacher, but my motivation for general student like you. Why do we study research methodology itself? Practical research, design and planning. So if you understand very basic knowledge about crystallography, just not using crystal as a black box, the difference is like this. You can plan and design. Design. My word for you is design. Black box crystallography cannot provide your role in terms of design. But if you understand very basic, not very comprehensive like the textbook, if you understand very basic behind crystallographic vocabulary and the transformational relation between intensity and density, you can design. Whole keyword is design for you. Can you design your experiment or not? That is the difference between black box crystallography and practical crystallography. I would like to say practical crystallography. Practical crystallography, you do not understand whole physics. You do not understand whole mathematics behind crystallographic theory. But still, you are functional to achieve your own goal in terms of your protein engineering and in terms of your crystal engineering. So it has design part. Okay. So for me, if I squeeze my motivation, articulation. I'm practicing crystallography for you as a teacher to allow you to speak something unspeakable, or to allow you to think something about unthinkable before and after. Crystallography is at the interface of, according to Robert Hoover, I talked about Nobel Prize laureate Robert Hoover. His title given at my former university, my graduate school, is like this: protein chemistry at the interface of physics, mathematics, physics. Physics, chemistry, and biology. Okay, that was at the interface. So articulation at the interface. I'd like to say interface. Articulation at the interface. You should be able to articulate the problem even without knowing whole details. This textbook too heavy to read everything. Also, this is too much to apply all the details. But I'd like to condense this book into single page as you have. Knowing the difference between one bar, P1 bar. That's all. If you are able to condense all knowledge you need to know from protein crystallography into single page, you can be very functional at the interface of physics, chemistry, and biology. Anyway, structure of protein should be based on chemistry. We talked about protein structure. We talked about bond length, bond angle, and dihedral angle or torsion angle last time from protein structure chapter. And we talked about crystallization in terms of obtaining crystal. It has some issue in space and time. So we can be at the interface of physics, chemistry, and biology. So in such a way, you can articulate your own language. You are sharpening your language skill at each discipline. So crystallography can be very interdisciplinary training. Okay, that is my motivation as a teacher, and my motivation for you. With the knowledge of protein crystallography, you can design your experiment. Even your knowledge about protein crystallography can be transferred to your knowledge of proteomics in terms of sample fractionation or some treatment. Also for you, kind of target protein in functional modification. Okay. Also, through such a process, you can discover some relevant or very interesting or exciting target protein, and you may want to know the structure. Okay. Once you identify some important proteins from your proteomic study, next step will be like that. Study the structure itself. of the target protein, and you can find something interesting. That is my motivation. Anyway, let's come back here. Here, as I told you, this is too much. But mainly, for later chapters in data collection, you may better to focus on difference between two columns and difference between these another two columns. Also, relation between this and this. As I told you, FHKL, IHKL, electron density function rho, and Peters function P. Okay? UVW can be same as XYZ in terms of its fractional coordinate nature, but we reserved different symbol for UVW, not because we are using different coordinate system, but because that has a different meaning. This is not exactly real space, this is Peterson space. Okay? But you can safely ignore PUVW because this is only for structure determination using rotation function and translation function. It's important in terms of deriving some theory in structure determination, but this is completely safe to ignore this knowledge. Okay, so it's okay not to know anything about Peterson, but just as a parallel, you can look at the symbolic differences. Likewise, here FHKL, IHKL, even you can ignore FHKL because in practice, we will never get FHKL directly. In practice, you will obtain IHKL. Okay? So, which column you need to focus from now on? In practice.
And rho XYZ.
Yes. These two we need to look at. IHKL from experiment. Rho XYZ as a structure. Okay? This will be our result. This will be our experiment. Okay? So you need to understand Laue group symbol. You need to understand here chiral space group, but you can say simply space group symbol. Okay? Space group symbol, Laue group symbol. Laue is the name of German physicist who discovered X-ray diffraction. Okay? But a space group is just generic name to describe three-dimensional periodicity. Okay? Let me now. So I have this. So we will focus on first column. Okay. Based on your understanding of first column, you can expand the other rows. I made a mistake. This is first row. You need to focus. The others, you can expand the others in this way. Symbol 2, 3, 4, 6. With the help of rotation 2, 3, 4, 6, you can expand the other 11. Okay? But right now, let's focus on first row. One comment here, lattice properties. How do you speak about first column?
A is not equal to B is not equal to C.
But I will read in this way. A is not necessarily equal to B, B is not necessarily equal to C, C is not necessarily equal to A. If you say A is not equal to B, B is not equal to C, it can be understood in this way. A should not be equal to B, but in reality, A can be equal to B. B can be equal to C.
But it should not be equal to be
Pardon?
in the first row.
First row, yes.
In the first row.
First
Like
row.
if we want such kind of properties from a crystal,
Mm.
it should be not A. The angles should not be equal to A. Should not be equal to B. Should not be equal to C.
That's the very point we are talking about. Let's focus on alpha, beta, gamma. Here, symbol is like that. Alpha shouldn't be 90 degree, beta shouldn't be 90 degree, gamma shouldn't be 90 degree. But that is not simply true. There is very misconception about crystallography. So, I'm repeating again. If you read this paper, the logic behind my telling is written, but I'll give you my own answer right away. Here, the reason why we had not equal to symbol, here we have 1, 2, 3, 4, 5. Total 5 not equal to symbols. Okay? But the reason why we had not equal symbols is not really because we should not have equality among ABC and equality among alpha, beta, gamma to 90 degree, but distinction with others. This one as an extreme opposite of first row. Okay? Here, would you read, Muhammad?
A may be equal to B, may be equal to C.
Thank you. Wrong. Perfectly incorrect. We have some bias because we are human. Think about the wrong answer you made. Literature research. Do you know why?
Because I studied the previous chapter, it was about literature review.
Exactly. Even I was biased. We are talking about the beginning question. This is very important in terms of human psychology, also learning psychology. Okay, let me go back here. Here, I was curious why I didn't look at the other answers. I just look at because the answer sheet that Sabah submit to me just contain this one, person, comments or starting a research of the literature, simply literature review. Also, I had a meeting with Sabah from previous chapter, so chapter 5 is planning research and chapter 4 was literature review. Review of related literature, like that, to be exact. But anyway, this is about this is topic from just previous chapter. Also, I am biased, so I was thinking in this manner: why literature review can be a wrong answer? Something curious. And it's saying. So I checked full questionnaire like this. Oh, I found third one. Converting a question into a clearly stated research problem. Okay? Oh, bingo. But I'm saying I have some misunderstanding the problem because I was biased with previous chapter. Likewise, Muhammad. When I explained the first row and again asked Muhammad about last row, he made some interesting mistake. This should be read in this manner: A, B, C exactly same. Okay. Also, alpha, beta, gamma necessary to be 90 degree, not maybe. This is compulsory. Okay. But at the first row, I said maybe or and not should be, so he made some biased answer. Okay? But anyway, this is compulsory. That is optional, not necessary. Okay? To distinguish triclinic case and cubic case, we made equality or non-equality. But equality, symbol inequality should be understood. Is not necessary to be equal. Okay? Such an explanation was done, very nicely done in the paper, teaching in this paper. And with such a concept in your mind, here, minimum internal symmetry. Okay? Minimum is not maximum. Minimum means the symmetry which should be present. Here, even triclinic, let's go back to triclinic, not to be confused. Here, triclinic. Internal symmetry. Even in triclinic space group, we can, it's not cannot, we can have or we may have internal symmetry. Internal symmetry. Minimum internal symmetry, none, but we may have internal symmetry. But such an internal symmetry may not be or should not be crystallographic symmetry. I'd like to distinguish these two. Internal symmetry can be two kinds. One is crystallographic internal symmetry. The other is non-crystallographic internal symmetry. It's okay to have non-crystallographic internal symmetry even within triclinic unit cell. Okay? But if it is not compatible with crystallographic packing, it can be non-crystallographic symmetry. That is another topic for later chapters. We have chapters about for molecular replacement. Actually, molecular replacement as a way to solve crystal phase problem is relying on internal symmetry, which may not be crystallographic symmetry. Okay, so here, anyway, minimum internal symmetry is none does not say that we should not have any internal symmetry. So it can be either crystallographic symmetry or non-crystallographic symmetry, but if we have crystallographic symmetry inside of unicell of triclinic cell, it should be upgraded to higher symmetry. Like in case of two-fold crystallographic symmetry, it should be monoclinic. If you have three-fold crystallographic symmetry, it should be trigonal. If you have four-fold crystallographic symmetry, it should be tetragonal. If you have six-fold crystallographic symmetry, it should be hexagonal. Three and four-fold coupled in summate, it can be cubic. But even we can have five-fold rotation symmetry, but it cannot be compatible with crystallographic packing or some periodic packing. So it can be symmetry in triclinic or even in other unit cell, but it cannot be crystallographic symmetry. It can be non-crystallographic symmetry. So I'd like to distinguish non-crystallographic symmetry and crystallographic symmetry. So here, let me come back here. Properties of cell parameters. Anyway, restriction or limitation. Actually, we do not need to have any kind of restriction on triclinic cell parameters. That is only the way to distinguish these 7 cases. Can you know the difference? Here,
rotation is different. Folding, rotation folding is different in every case. In every case, rotation of folding is different.
Yes. Internal symmetries are not the same.
Yeah, internal
internal symmetries are not the same. So what is, in terms, science has cause and effect. Sorry. Simply, I'm introducing this word for you. I'm giving you these two words, cause and effect. In science, when we design something, depending on design, we are expecting some result. Likewise, in terms of symmetry or in terms of cell perimeter limitations, we have cause and effect. What is cause and what is effect in these two columns?
The first one is cause and the second is effect.
You said this one is cause, this one effect. What about which way?
I think
opposite. Swiss.
Effect
Yeah.
and cause.
Yeah.
Bingo. So this is result of this.
Yeah.
Okay? That is very misconception you should remove. This is not cause. This is cause. Because of this cause, we have this kind of effect. Okay? So because this is effect, this is arbitrary, actually, triclinic case, arbitrary. But because no cause, no effect. Okay? None means no cause. No reason why we should have limitation here. So no cause, no effect. But here, strict cause or strong cause, actually, for three-fold axes along space diagonal, actually we may have some more. Four-fold, something are not correct here. Cubic has two kinds, 2, 3, 4, 3, 2. Actually, we should have tetragonal, but this is about minimum symmetry. Let's recall this, minimum. Maximum is like that. Fourfold, we have fourfold rotation axis along fourfold rotation axis perpendicular to face. We have cube, on each cube face, cubic face, we have fourfold. So this is a minimum, also minimum, minimum, minimum. So minimum cause, minimum effect. Okay? No cause, no effect. Okay? So these are cause, these are effect. So effect should be followed by cause, not cause, not effect. I have some problem in terms of tongue. Let's have some pause. Okay. 잠깐 좀 쉬죠. 물도 마시고. Can you get main idea? I'll take 10-minute break, so you can feel something, not forgetting anything. Even you can start to save your time to go home. Let's come back to our story again. You can take time later for kids. Let's come back to the education paper. And in the introduction section, there is word hieroglyph. Do you know this word? This word has something in Rosetta Stone, Egyptian ancient alphabet for Egyptian, and hieroglyph and Rosetta Stone, space group and protein crystal. Stone and crystal, Rosetta and protein. This is kind of funny analogy between any difficult symbols. This was very difficult for British scientists to decode the meaning. Once it was decoded or understood, we cannot say full, but some history of ancient Egyptian can be understood. Likewise, space group symbol, without having knowledge about crystallography, it can be like Rosetta Stone. But once understood, we can design our protein structure. Not only having protein structure from native one, we can design our mutant one to improve its function, as we are doing for fluorescent proteins. Not only green fluorescent proteins, we are working for red one and cyan and variety, many colors. Okay, and so Rosetta Stone protein crystal, and protein crystal, we have intensity and density. This is the main difference between Rosetta Stone and protein crystal. Protein crystal, we are not directly looking at density. Electron microscope, we are actually looking at density directly. But protein crystal, for X-ray diffraction, we are obtaining intensity at first hand. Then we are converting corresponding density through Fourier transform and phase solution, or solving phase problem in crystallography. So we have some dual information here. Unlike Rosetta Stone. Rosetta Stone, based on internal structure of whole paragraph or whole story written in Rosetta Stone, they decoded meaning based on occurrence of frequencies and their knowledge about ancient Egypt. But what we are decoding here is based on intensity. We can directly measure intensity. We should solve some missing information phase, and such a missing information phase can be derived based on our knowledge about chemistry, atomicity or connectivity of protein, like alpha helix or beta sheet. Then we will obtain density. So intensity and density are coupled. But what I found from this paper is like this. It approached the topic like Rosetta Stone, which has only one side, like density. Density directly, it's not possible to look at using X-ray alone. But we should look at intensity, and intensity in some way should be related to density. Such a link is not discussed at all in this paper, because this paper is dealing with only real space. Volume A for real space, volume B reciprocal space. We have separate volume, like a separate chapter in this book. They have separate discussion about real space and reciprocal space. But I did try to combine two separate concepts for you, intensity and density. So now come back here. Here, you try to answer some relation from first row of this table, but I'd like to introduce this concept. This is sphere, three-dimensional sphere. For the sphere, what do we have to describe its volume or its dimension?
Diameter.
Diameter for circle, and we have another word.
Radius.
Oh, radius. Diameter is 2 times of radius. I'm sorry. Diameter is also valid one.
And perimeter.
Yeah. perimeter is 2 pi times radius. Yeah. Perimeter this way, diameter this way, right?
Yeah.
Radius half of diameter. I'm sorry. But here, 1, 2, 3, 4, 5, 6, 7. Column 7, we have description on the range of HKL. Could you read the range, Muhammad? How can you read?
Which one?
7th column, under the title of asymmetric reciprocal unit. You can use your own printout or textbook.
H infinity to infinity.
Minus infinite to plus infinite.
Okay. H minus infinity to plus K minus infinity to plus infinity. I 0 to infinity.
That should be I.
Oh, sorry, L.
L.
HKL.
So instinctively, from now on, you should say HKL, not I. Okay?
HKL.
L, 0 to infinite. Then
Exclude 0 KL if L is less than 0 and 0 K 0 if K is less than 0.
yes, that's all. Then first of all, here asymmetric. We have only word asymmetric there. First of all, what does the word asymmetric mean?
Asymmetric, having no symmetry.
Correct. No symmetry, asymmetry. Okay. So asymmetric unit means non-redundant one. Then for triclinic, we have unit cell which does not contain any non-internal symmetry. So unit cell of triclinic should be an asymmetric unit. Is that correct? I'm saying something about real space unit cell. Also, I'd like to make comparison between real space unit cell for triclinic, also reciprocal space unit cell for triclinic. Anyway, I'm talking about something about triclinic, but I'm trying to draw your attention to both cases. One is real space, the other is reciprocal space or diffraction space. In this case, reciprocal and diffraction are same. I'm talking about range of x, y, z. Let's add some column like this. Asymmetric unit, not reciprocal unit. Here, asymmetric reciprocal unit, we have conditions like this. If you look at the rest one, H 0 to infinite, K 0 to infinite, L 0 to infinite.
Not
No, sorry. Here, orthorhombic. Let's look at. Oh, you are very smart to catch my own mistake. You are almost at the level of expert, like me. I caught many mistakes in textbook, also mistakes from this paper. Now you are catching me. Orthorhombic. There is orthorhombic. Orthorhombic. I was talking about orthorhombic. H 0 to infinite, K 0 to infinite, L 0 to infinite. This case, I'm correct? Yeah, I'm correct. Thank you. Here, cubic, unlike orthorhombic, little bit tricky. H to infinite, K to infinite. Okay, different because of higher symmetry than orthorhombic. This is orthorhombic. Okay, so for simplicity, for comparison, let's come back here with the figure like this. This is for orthorhombic in reality. If you look at the other chapter, which contains this figure, I took from chapter 8, maybe, I'm not sure. But we have symbol like this, 2 over m, 2 over m, 2 over m, actually, which is the symmetry of orthorhombic. Orthorhombic, I said, this is a little bit long, 2 over m or 2 over m, 2 over m, 2 over m. That is the symmetry of orthorhombic in diffraction space. Laue group, diffraction space, intensity. Okay? But what about symmetry of orthorhombic in real space in terms of range of x, y, z? You need to think about that. Also, even simple case, 2 over m, h minus infinite to plus infinite, k 0 to plus infinite, l 0 to plus infinite. That case, we have 2 over m symmetry. But in real space, we have P2 symmetry. Under the symmetry of P2 or P2 sub 1, we have limitation on the range of x, y, z in terms of asymmetric unit cell. Here, we are only talking about asymmetric reciprocal unit cell, but we can also talk about asymmetric unit cell, not just asymmetric reciprocal unit cell. We have 2 unit cells. For density, simply we are saying unit cell. Unit cell. For this, we are saying reciprocal unit cell. But here, if you are clever to catch my own mistake, which word should I remove? Unit cell and reciprocal unit cell. Oh, could you explain why?
Because cell is in the crystal form. Crystal is not in reciprocal.
Closer, but not quite perfect. I'll give a chance for you, Sabah. You're very close to perfect answer, but not quite perfect. You use my own term, but recall what we discussed before, and last time we talked about P1 and 1. At that time, we talked about some symmetry, which is very intrinsic in all kinds of crystal.
Translational symmetry.
Yes, translational symmetry. We are missing translational symmetry in intensity space or reciprocal space. So cell is a repeating unit. So we are saying unit cell, unit of such a periodic arrangement. We still have unit in reciprocal space, but in reciprocal space, we do not have some periodicity. What kind of character or characteristics do we have instead of periodic arrangement?
In the reciprocal?
Yes, or diffraction.
Dots.
Spots. Continuous functions are converted into spot in reciprocal space. Not continuous form, but function only at the spot, at each HKL. So it's better to remove cell here. Cell is a basic unit in real space, but cell is reserved for repeating unit. But here, reciprocal unit will not be repeated with overlapping function. Okay? So reciprocal unit is better word rather than reciprocal unit cell. But reciprocal unit either can be asymmetric, within unit cell, we can talk about asymmetric unit cell. So asymmetric unit cell should be less than or smaller than unit cell, because out of asymmetric unit cell we can let me explain. Anyway, unit cell has something with translational symmetry, but what kind of symmetry will link between unit cell and asymmetric unit?
Internal symmetry. Rotational symmetry.
Yes. Not only rotation but also screw.
Screw axis also.
Yeah, screw. Okay. So asymmetric unit. I'm sorry. Asymmetry. Asymmetric unit cell is not a unit cell. It should be smaller than unit cell. But in case of triclinic, unit cell can be asymmetrical unit cell. That is only for triclinic. For other than triclinic, monoclinic, it should be half of asymmetric unit should be half of total unit cell. Also for orthorhombic, it can be 1/4. But if you look at coverage of R square, how can I say? Here, another symbolic problem. There, this extra column is for coverage of R star. R star means reciprocal space as a shorthand. Then we can speak something about coverage of real space in terms of asymmetric versus total unit cell. Then we can add some column like that, coverage, or how can you say? I'm trying to say something about ratio between unit cell volume and asymmetric unit cell volume. So if you say asymmetric volume of asymmetry divided by volume of unit cell.
Ratio of asymmetric.
This is the ratio I'd like to talk about. And here, coverage of R square is like that. But that's not for unit cell, but that's for reciprocal unit. This is another thing. I do not have proper terminology yet. I cannot recall the name of this one, but the coverage of R star is like this. Volume of asymmetric double S or single S?
Just single.
Is that single?
Single.
Is that single? Yes, you are correct.
Double M.
Sorry, I made a mistake. You caught another mistake of mine. Single S, asymmetry. Volume of asymmetric double M or single M? Double M. Asymmetric reciprocal. Here we have something extra. Reciprocal then no cell, just unit. Divide by volume of reciprocal unit. Is that correct? But here, then I have another problem in terms of explaining the concept. Here, volume of asymmetric unit cell, even asymmetric unit cell, makes sense. Also, volume of unit cell makes sense, but volume of reciprocal unit, actually, it shouldn't be a unit. What I'm saying is sphere. Also, some part of sphere. How can you describe sphere and some part of sphere in this case? It cannot be reciprocal unit. I have some difficulty in terms of using reciprocal unit for this particular column to describe the range of HKL. It shouldn't be reciprocal unit.
Space.
Better word can be sphere. Here, I have some disagreement with the word choice of unit there. Unit is like this. Actually, this unit, if I say A star, actually this cannot be A star. This should be A star. This length, A star. B star, this length. C star, this length. Then this one can be called 100 spot name, HKL in terms of HKL. 100. This one should be called as 010. Then this one will be called as
001.
Oh, bingo. It should be called like that. Then this can be regarded as a unit for reciprocal space. This is unit. Such a unit can be related to A, B, C in reciprocal way. If this rank is A star, one of A star can be A. Vice versa. B star should be 1 over B. Okay, so B should be this is kind of collaboration. This is not only my work, this is also your work to improve terminology in this table. Before this, I thought reciprocal unit is kind of acceptable terminology, but I found something wrong in this usage because here we have wrong impression about unit. Unit should be like this, simply wrong application of unit. So range is actually is not about unit, but range is about sphere.
Sphere or space. We can use the word space instead of unit.
That is my difficulty to explain something without introducing concept of resolution. We talked about resolution last time. Resolution as a radius for this kind of sphere. In the textbook, we have two kinds of sphere. One is limiting sphere, the other is Ewald sphere. Ewald is the name of German physicist who described X-ray physics in terms of this kind of geometry. But right now, let's forget about Ewald and let's forget about limiting sphere, but let's think about sphere in this way anyway. Also, let's come back to this figure. Here. Okay. Here, x, y, z in terms of fractional coordinate can be between 0 and 1. in terms of lengths of A, B, C respectively. But HKL can be negative infinite and positive infinite. But if you think electron density in terms of resolution, so I told you, we have radius here, okay? Such a radius can be described in terms of sphere, because with the given radius, we can draw sphere in 3 dimensions, circle in 2 dimensions. So for the given resolution in angstrom, we can have reciprocal resolution in angstrom inverse. Then we can construct such a sphere or circle in 2 dimensions and sphere in 3 dimensions. Okay? So in reality, I'm talking about real experiment, we cannot have minus negative and plus negative. Always we have maximum H, minimum H, maximum K and minimum K, maximum L and minimum L. Normally, for the given X-ray, we have equal H maximum and H minimum in terms of its amount. We just have opposite sign, minus H max plus H max, okay? Minus K max plus K max, minus L max plus L max. They will be related to resolution, D, okay? And if we accept such a basic fact about resolution and as a result, sphere as a way to describe all the available HKL spot within given radius, then we can talk about range of available HKL or range of asymmetric reciprocal space. We can say either space or sphere, but in this case, only sphere. So here, volume of asymmetric reciprocal space or sphere. I'd like to say sphere as a default answer. And volume of reciprocal unit, not unit, but sphere. So that is not clear in the table, but I'd like to introduce concept of sphere in both places. At the place of unit cell in reciprocal, unit cell in real space was converted in sphere in reciprocal space. Can you follow me, Muhammad? Why we need this kind of introduction of the word sphere?
Because unit cell doesn't exist in the reciprocal space. So that's why we cannot use unit cell in the reciprocal space.
In reciprocal space or diffraction space, we do not have any translational symmetry. We just have spot-like character of each observation. So I'd like to avoid the word unit cell or unit. But still, we have some unit in this way. Unit amount of repeating spots. Space between each spot has some A star periodicity. Distance between each spot has B star. But this is only valid in reciprocal space. If I make some complications, diffraction space itself is not reciprocal space. That is kind of distorted reciprocal space. We have some complication there. But first of all, if we reconstruct such a diffraction intensity, not in detector space, but in reciprocal space, we can imagine data in sphere. So I would like to prefer the word sphere here. So let me make some conclusion, quick conclusion. We can think about range of x, y, z triclinic XYZ is between 0 and 1. But higher symmetry may result in reduced area as a asymmetric unit cell. Likewise, reciprocal space, we have such a reduced symmetry, but not in terms of unit cell, but in terms of sphere. In this figure, we have 2 over m, 2 over m, 2 over m symmetry. Okay, there. But in terms of higher symmetry, and 2 of m, 2 of m, 2 of m, that's what I was talking about. In terms of triclinic, 3 bar. In terms of other symmetry, in higher symmetry in trigonal, 3 bar m1 or 3 bar 1m may result in other way. So difference between 3 bar and 3 bar m1 is like this. This area is unique. In terms of whole sphere, this is asymmetric sphere. But if we have extra symmetry, mirror, then upper part and lower part will be equivalent. So in terms of Raoult group 3 by M1, only upper part will be unique. Likewise, if we have no internal symmetry, if we have only triclinic symmetry, upper sphere, whole upper sphere will be unique. Even in the point group 1, whole sphere will be unique. Each intensity of IHKL will be different. But if you have inversion symmetry, upper part and lower part will be related by IHKL. This is basic symmetry of diffraction space. I'm talking about value of intensity on particular HKL. IHKL can be equal to I minus H minus K minus L. This is so-called Friedel law in X-ray crystallography. If we have this kind of inversion, then we have unique area for upper part. This is what is written here. L 0 to plus positive. But as I introduced, we should think not in terms of infinite, but in terms of sphere. Okay? Can you follow here? I'm making some corrections in textbook. What I'm trying to emphasize is sphere model for diffraction space or reciprocal space. Without having sphere model, we can be confused. But I'm worrying about the confusion I introduced today because I'm not talking about textbook story. I'm talking about practical data collection. Also, it has some reasoning due to some physics principle. In physics principle, we should have a model based on observation. Observation cannot be made from minus to plus infinite. Observation can be made with finite H maximum down to minus H maximum. H maximum can be determined by Bragg equation, which I didn't describe yet, but it can be studied at later chapter for data collection. I will not make some complication due to Bragg law, but take the word resolution with me. Did I have such a figure? I didn't have such a figure today, but from chapter 1, we have this figure and corresponding figure at varying resolution. High resolution, medium resolution, and low resolution. Depending on resolution, we had visible ranges accordingly. High resolution, larger K and H. Low resolution, low K and H. Meaning H maximum, H minimum, this way. Here, H maximum minus H maximum. K maximum minus K maximum. So we can decide some resolution sphere. Okay? That's the concept I'd like to share. So for the given resolution sphere, we can talk about asymmetric sphere. This is a figure like this. Asymmetric sphere of 2 over m, 2 over m, 2 over m is just 1/8 of total. This is 1/8. Upper sphere is 1/2. Half. Among upper, this is 4 of such upper. So total 1/8. Okay. That is the column for coverage column. Here, coverage of R square is like that. Orthorhombic is 1/8. Okay. Likewise, even triclinic, not 1, but 1/2. Why 1/2 is like this? IHKL can be equal to I intensity at minus H minus K minus L. Because of the nature of diffraction. Diffraction, unlike physical mirror, molecule as a mirror, electron density mirror, either phase can be equivalent. This side can be equivalent. Unless we have some anomalous dispersion. Okay? That is another technical term I didn't introduce yet, but let's focus on very basic. Here, coverage of R can be understood in this manner. R star basically reciprocal sphere. Okay, let's call R star as a reciprocal sphere. This is our invention. Let's call R star as a reciprocal sphere. Okay, reciprocal sphere. Also, such a concept was already presented in the textbook in terms of its unique area in reciprocal sphere here in this figure. In this figure was given in later chapter 8, I think. But such a concept should be already learned at this stage. Otherwise, you may lose some important connection or linking. I'd like to establish main link in crystallography. Link between real space and reciprocal space. Okay. So here, even triclinic, Rawi group 1 bar, we have some equivalent part. Upper sphere and lower sphere can be related with this equation. But if you have 2 over m, 2 over m, 2 over m, only 1/8 is unique. Here, 1/2, half is unique. Likewise, 3 bar M1 have this kind of unique area, so-called, we call it asymmetric reciprocal sphere. So actually, asymmetric part is not sphere, part of a sphere. Likewise, asymmetric unicell is not unicell, part of unicell. Such a part of unicell can be related to other part with symmetry element. Here, symmetry element is like this. 2 along A star, 2 along B star, 2 along C star. Also, M perpendicular to such twofold, M perpendicular to such twofold along B star, M perpendicular to twofold along C star. Actually, we have 8 symmetry elements here in this Laue group 2 over m, 2 over m, 2 over m. Basically, 2, 2, 2 along A, B, C, also A star, B star, C star, M, 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 perpendicular to such a plane, A, B, C, also non-symmetry 1 and inversion symmetry 1 bar. 1 always present because 1 is nothing new, always present as a translational. Not translational, just a symbol identity. And 1 bar introduced by combining 2 and m. Okay. So actually here we have 8 elements of symmetry operations. As a result, we have 8 equivalent parts. This part, lower part, and this part, this part, this part. Upper hemisphere we have 4. Lower hemisphere we have another 4. Total 8 unique areas. Such areas are related with symmetry element, like a two-fold symmetry or mirror symmetry, or symmetry of 1 as an asymmetric, and symmetry of 1 bar as an inversion related one. Okay. So I explained everything about. I'm sorry. Coverage of R, and what didn't I explain at all? I explained range and coverage. What you need to learn more, Muhammad, or
column number 5.
1, 2, 3, 4, 5. 5? Point group multiplicity. Point group multiplicity has something with coverage of R square, R star. Actually, they are identical or not? Here we have difference. Point group and inverse number or reciprocal number coverage R should be doubled. For every case? Yes. Yes, every case. Here, same and same. So, point group multiplicity, we can call it based on symmetry element present in point group. Then we can say, according to this terminology, we can say Laue group multiplicity for the reciprocal number of these. If we take reciprocal of this, particularly for row 1, first row, we can say number 2, then number 4, number 8, then another 8, and 16, 16, 6, 12, 12, 12, 24, 24, 48 maximum. Then always this column is double of this column. Okay, so what you can learn from this is reciprocal of coverage of R square, R star is multiplicity of Laue group. So multiplicity of Laue group is related to multiplicity of point group by factor which number? I'm asking you. What is the difference between point group multiplicity and Laue group multiplicity? Which factor should be? Double. Two or double. Okay. So coverage of reciprocal sphere can be understood under the light of multiplicity of Laue group. What I mean by the word multiplicity is we can introduce multiplicity in this way. Anyway, the reason why we have double because of this. In Laue group, always we have this inversion. Because of addition of inversion element, we have double multiplicity. But in terms of multiplicity, how can you define multiplicity? Muhammad, multiplicity.
To be multiplied.
Multiplicity of point group and multiplicity of Laue group and multiplicity of some group. Multiplicity of point group, multiplicity of Laue group. We can define multiplicity of which group? We can define multiplicity of group in this way. A number of symmetry elements. I said elements. Here, multiplicity of point 1 is 1, but multiplicity of Laue group P1 is 2. Why 2? One is only has symbol 1, but 1 bar has 1 and 1 bar. 1 is for basic identity symbol, symmetry element for nothing, no operation, and 1 bar as an inversion. Actually, it's not clearly explained in the textbook, but in terms of symmetry element, point group 1 contains 1, nothing else. But point group 2 contains actually 2. Why 2? Not just single.
Because it is half distance, 2-fold.
No, you should say 1 and 2. I'm talking about element of, first of all, this is group is a mathematical term. Group is kind of special set, collection. So we can talk about its members. So member of point 1 is only 1. Because the word 1 is the same, we have some confusion. I repeat. The name of point group 1 is 1, right? It's easy. So the point group 1 has its member element.
1.
The element is also 1. We have some confusion. I'm sorry about this confusion, but because of this kind of confusion, crystallography is difficult. But elements of crystallography language are very simple, very limited in terms of vocabulary. But we are using same vocabulary in different contexts. That is the source of difficulty of crystallography. We have lots of redundancy in terms of vocabulary and terminology. Here, 1, point group 1 has element of 1. This is symmetry symbol. This is point group symbol. 1, 1 are not the same. This is symbol of group. This is element of such a group. This 1 is identity operation. If we are specific about terminology, identity operation. This is operation 1, which means no operation at all. This is group symbol. This is group symbol, this is operation symbol, or symmetry element. And likewise, 2 contains 2 elements, 1 and 2. This is space group symbol or point group symbol. This is symmetry element 1 and symmetry element 2. Likewise, 3 contains 3. Not 3. 3, but 3 is a little bit different. 3 is 1 and rotation by 200. How can I distinguish this? I don't remember. Anyway, let me write down. Even as a teacher, I have difficulty to distinguish these things. This is like difficulty to explain something which cannot be explained easily. Symbol 1 in terms of rotation is 360 degree rotation or 0 degree rotation. Likewise, point group 3 actually contains 3 independent ones, like twofold. Twofold contains, point group 2 contains 1 and 2, which means 0 degree rotation and 180 degree rotation. But here 3, 0 degree rotation, 120 degree rotation, and 240 degree rotation. If we have 360 degree rotation, then it will be identical to 1. So how can I distinguish 120 degree rotation and 240 degree rotation in terms of its symbol? How can I say that?
1 by 3 and 2 by 3.
1 by
3
X, Y, Z.
and 2 by 3.
1 by 3 and 2 by 3. I'm not sure about that. That can be your own exercise and my exercise. But if we are talking about 3-pole screw, we have way to distinguish these two. 3 sub 1 and 3 sub 2. And 3 can be identical to 1. Okay? In terms of space group P3 sub 1 or P3 sub 2, we can have screw like this, 3 sub 1, 3 sub 2. But in point group 3, it's better to have terminology like this, but I cannot remember what we can have in terms of distinguishing these two rotations, 120 degree rotation and 240 degree rotation. But anyway, in point group 3, we have identical operation or no operation as a symbol 1. Also, we should have 3-pole rotation by 120 degree or 3-pole rotation by 240 degree. Okay. Multiple of these 3 can result into same one. If you multiply, if we apply 120 again, it will result in 240 degree rotation. If we do more, it will result in 360 degree rotation, which is identical to nothing or no operation. That is the nature of rotation. And likewise, number 6 or point group 6 has multiplicity of 6 in that manner. Also, pole has pole multiplicity of pole in that manner, in the same manner. Okay. But upon that, we can have inversion, so we can have doubled multiplicity in Laue-group. Okay. But for tetragonal, we have something extra because of presence of some interaction between 3-pole and 2-pole, even extra presence of 4-pole. Depending on such extra symmetry, we have multiplicity up to 24 in QB. If we add inversion, we have multiplicity up to 48. But in orthorhombic case, we have up to 8 in 422 and 4 over MMM or 4 over M, 2 over M, 2 over M. We have 16 as a maximum multiplicity. Okay. I'm sorry if I did introduce some confusion, but why did we talk about this kind of multiplicity is to make a comparison between point group multiplicity and Laue group multiplicity, and Laue group multiplicity is reciprocal of coverage of reciprocal sphere, as we introduced as a new vocabulary. Okay, So make some link. Then this kind of marginal issue can be forgiven. Anyway, I admit that I had some limitation in terms of distinguishing these two, but we may have some mathematical way to distinguish these two. I forgot something about that. Okay. And what else? Anyway, lattice parameter as an effect due to internal symmetry as a cause, and crystal system, this is English word, so if you are familiar with data collection, you will automatically memorize something, but basically triclinic is general case, so it can be tilted in every way. So tri means three directionally inclined, but it doesn't have to be inclined as necessity. It can be inclined as a general case. Also monoclinic, orthorhombic, tetragonal has something with internal symmetry present as a fourfold, threefold, sixfold respectively, tetra, tri, hexa, and orthorhombic has something with orthogonal, and cubic, as you know, cubic as a perfect polygonal. Sorry. So this terminology, you may be familiar with crystallography, then you can recall what it meant. Okay? And point group, in terms of distinguishing 3 and 3-2, 6 and 6-2-2, 2-3, 4-3-2 may not be easy, but 1, 2, 2-2-2 can be understood in simple way, like symmetry along ABC. There, 2 can be understood in 3 ways, depending on its setting. 2-1-1, 1-2-1, or 1-1-2, depending on choice of unique axis. Because of choice of unique B, this can be called as a 1-2-1. Okay? So from triclinic up to orthorhombic, story is simple like this. We should think about in terms of ABC. So even for triclinic and monoclinic, we can expand same manner like orthorhombic. 1-1-1 can be understood. Now 1 can be understood 1 along A, 1 along B, 1 along C. So 1-1-1 can be an extended symbol for 1. Likewise, 2 can be extended, simplified symbol for 1-2-1 in this case. But generally, 2 can be put in 3 different ways, depending on the choice of unique axis. 2-1-1 or 1-2-1 or 1-on-2. But 2-2-2 are unique because we have this kind of restriction or limitation. So 2-2-2 fixed with respect to ABC, but still we can choose different ranks of ABC by permuting the ranks of ABC anyway. Okay? But 4-2-2, 3-2, 4-3-2, and 6-2 will be fixed with the symmetry. So anyway, that is about point group symmetry, and point of multiplicity can be understood in this manner. Symmetry element present there. Also, this will result in the number of equivalent position in terms of XYZ. Electron density rho XYZ can have equivalent position related with a symmetry element present in unit cell. Okay? And Laue group. Laue group, we talked about Laue group in terms of limiting sphere and in terms of the unique area and coverage. And what else?
We have Bravais multiplicity also.
Breve is another name. Breve is French name. Breve multiplicity. Where do you have Breve multiplicity? Yes. Breve multiplicity. Forgive me, please. This is too much. But right now, primitive is 1. Okay? take primitive 1 as a simple understanding. But beyond that, we have C centering 2, I centering 2, F centering 4. What else do we have? Rhombohedral 3. What else? 4. So face-centered always 4. I and C has 2, rhombohedral 3. So you can memorize in such a manner. But this has also with number of equivalent position, okay? Like number of symmetry element. But number of symmetry element has something with point group, but Breve lattice has something with translation. This has something with rotation or screw, but Breve has something with translation. So depending on the symmetry element present in unit cell, we should introduce Breve lattice or Breve multiplicity. So right now, I'll not explain anything about Breve multiplicity, but depending on Breve type, you can deduce proper multiplicity. Simply, primitive is no specific symmetry in translational, so simply 1. But C centering and face centering has number 2 and 4 respectively. Also rhombohedral 3. See? Nothing else. Then we explain everything. So you can finish your own answer sheet now because we talked about everything. But before starting your answer, I'll talk about a little bit what I didn't explain or what I didn't cover today. That will be topic for next session, actually for next semester, but in between I'll prepare some video material, not lecture material, but kind of supplementary material, supplementary video material. From that, last time I talked about resolution, also refracting plane. How to construct refracting plane based on HKL index. That has something with concept of diffraction in terms of refraction. Also, it has very practical in terms of resolution in crystallography. Resolution in crystallography is so central, even in terms of building electron density. So it should be understood properly. But today, I will not talk about further. But anyway, there is another missing link. So firstly, I focused on linking between crystal geometry and diffraction basic in terms of IHKL and rho XYZ. That's the main topic I did today. But also we need to link DHKL or D star HKL. Even if I briefly mention the textbook story, this is not part of your question and answer, but this is my mention about textbook mistake or simply difficulty of teachers. Okay. Here, anyway, DHKL, D star HKL, very simple relation. Simply reciprocal in numbers, not reciprocal in vectors. A, B, C, A star, B star, C star as a vector, they are reciprocal to each other as a vector, not as a number. Only in orthorhombic setting, A star number, length of A as a symbol italic A can be reciprocal to A star. So what I'm saying is you need to understand. these two main concepts, reciprocal concept and Fourier transform pair. The symmetry concept I did talk about today is to link electron density and its corresponding IHKL. So we have different coordinate system. That's the concept I'd like to link. Here, unit cell should be some triclinic cell. And here, sphere. How can I say? Sphere. Okay. Fourier transform relate unit cell content with diffraction data, which can be mapped inside of this kind of sphere. That's the concept I'd like to link. Fourier transform pair, actually. Electron density, and intensity. That's the main effort I did today. But simple things, but also something practical in data collection is reciprocal concept. Reciprocal concept, vector A, B, C, these are vector, can be reciprocal to A star, B star, C star. But such a reciprocal vector, we need mathematics to explain the relationship. But in simple case like orthorhombic, alpha, beta, gamma equal to 90 degrees, then we have simpler relation like A star is equal to 1 over A and B star is 1 over B and C star is 1 over C. This is only valid in the case of orthorhombic, not valid for triclinic. But if angle alpha beta is close to 90 degrees, this can be close to this relation. So unit cell length A star B star, reciprocal unit cell A star B star C star, or reciprocal vector length A star B star C star has reciprocal relation like this: 1 over A, 1 over B, 1 over C. Likewise, resolution D can have this kind of reciprocal relation, but in terms of HKL, particular DHKL, spacing of refraction plane, can be calculated. And in the textbook, for orthorhombic case, orthogonal system means orthorhombic. This upper form, complicated one, can be simplified to this case, but this is simply wrong. If you plug 1, 0, 0, then B squared over 0 can result in infinite. Simply, we cannot even calculate 1, 0, 0. So correct one is like this: H squared A star square plus this one, and cross term, their gamma star is actually gamma in orthorhombic, because gamma, alpha, beta, gamma should be equal to 90 degrees. As a result, alpha star, gamma star, alpha star, beta star, gamma star should be all equal to 90 degrees. As a result, cosine term should disappear. So we do not have any cross term there. So we have only this part for orthorhombic. So also, if you use this simple reciprocal relation, then instead of A star, we can put 1 over A. As a result, H over A squared, K over B squared, L over C squared. At the outlook, this can be similar to this one, but in reality, if you pay attention to details, this one reciprocal. But if you invert this, this is 1 over this, not this. This and this are not identical. So in the textbook, something wrong. So you should use this formula. If you plug number 100, 1 over a square, okay. 0, 0, 0, nothing. So 1 over a square, then square root actually is 1 over a. So DHKL become a. That makes sense. D100 should be equal to a. Likewise, if you plug 010, what will be the answer? I'm asking your answer. This is practice. I'll repeat my own as D00 was equal to A. Then what will be answer for this one? D010. What will be your answer?
B.
B. Oh, correct. Then what will be 001? C. But if you plug these cases, 3 cases, we do not have answer, no answer. Problem. But if you plug this number into my equation, we can immediately get intuitive answer like this. If you take star there, we can put star there. And simply this is 1 over A, simply 1 over B, 1 over C. So if you go back here, that makes sense even in figures like this. Where is this star 100 is like this? Actually, we are pointing here. 010, we are pointing here. This is distance. This is distance, 1 over A. This distance should be equal to 1 over A. This distance should be equal to 1 over B. This should be equal to 1 over C. So, understanding reciprocal relation in this way, we should be able to link real space length and reciprocal length. Also, real space refraction plane and reciprocal space refraction spot, so-called Bragg spot. Okay? That's the topic I didn't describe in full manner, but if you catch both things, Fourier transform pair concept and reciprocal space pair concept, you understand very basic concept of crystallography. Fourier transform relation and reciprocal relation. Okay? I'm done. Anyway, as a quiz, you will answer from the perspective of Fourier transform pair, even though I didn't use the Fourier transform pair. Okay? Under the light of electron density function and intensity data, you will describe your understanding. Okay? Later then, for data collection and later chapters, I will repeat this again.